Hello everyone, I'm Dr. Gill and welcome to my channel Physics by Dr. Gill. In our previous lectures, we studied how Aristotle's law of motion failed to explain reversibilities of law of physics and how Newton's law of physics explain this reversibility phenomena, and how from Newton's simple equation of motion we can predict past as well as future. We have taken very simple examples of spring and circular oscillating motion to prove it. In today's lecture, we will study a little bit about conservation laws. If you could recall, I have discussed very simple laws for coins and dice in my previous videos and talked about conservation term there. I have told that conserved quantity is simply the number that we have invented through our trajectory, which is simple for one cycle. Like in case of dice, we made 2 cycles and we have given the number 0 or 1 or 2. If we made 3 cycles, then we can given the number 1, 2 or 3. And then if we start with conserved quantity 1, it stays at 1 and so on. But in circular motion that we have studied in last lecture, the motion of particles is in cycles that go round and round. And which quantity is conserved in this circular motion that we will discuss today. Let's discuss about it. Here we can say that all motion of the particles are in cycles. Suppose this is one cycle, this is second cycle, and this is third cycle. And suppose one particle is here, then the motion of the particles are in cycles. These are different cycles and you never jump from here to here or here to here. But if you are here, then you will move here only. And if you are here, then you will move here in this cycle only. It seems that there is some conservation law here or conserved quantity here. How can we describe it? This orbit cannot jump to this orbit, and so we can describe there are different orbits, and here is one quantity which is conserved. Let's discuss about the same. We have defined in our previous lecture, this is x and p's plane. P is also written as x dot. And we have defined in our previous lecture, if this is theta and particle is here and it is here at t0 time, initial time, then come here at t time, then we have found in our previous lecture that x is equal to, if this is c, radius, c cos t minus t naught. And what is p or x dot? It is equal to minus c sine t minus t naught. So this quantity, if we will find c square, then it will be x square. If small x, then small x. If we will take capital X, then it will here x square plus p square. How? If we will do c square cos square t minus t naught plus c square sine square t minus t naught, and the answer will be c square. It means c square is equal to x square plus p square or x square plus x dot square. We have a name for this quantity and it is called energy. How it is called energy? We can say that here if we will take c square as x dot square, because p is equal to x dot square, so we can write it as c square is equal to x dot square plus x square. x dot square, p square की जगह आप क्या लिख सकते हो, x dot square plus x square. So you can also write it as m by 2 x dot square plus 1 by 2 k x square. We have said in our previous lectures m is equal to 1 and k is equal to 1. Then what is c square? C square is just x dot square by 2 plus x square by 2. So it means different orbits. Suppose this is one orbit, this is one orbit, this is second orbit, this is third orbit. Suppose its radius is a, its radius is p, and the radius of last cycle is c. So different orbits of different radii correspond to different values. What is c? C is the radii. c यहाँ पे क्या है? Radii. हमने radius ली थी इसकी c. c is the radius. तो c is equal to हमने ये find किया. What is this? This is energy. So it means different orbits have different radii and different value. So the beauty of the harmonic oscillator, it is a harmonic oscillator, that it is a theory of phase space. Why theory of phase space? Because it is a graph between the x and p. X and p is the phase space. That where the oscillator or where the simple system carries out circular motion in phase lengths of different radii correspond to different energy. And all they had to do is vary the energy. If you will start from here, इसकी रेडिया, इसकी आपकी एनर्जी अलग है, इसकी अलग है, इसकी अलग है. If you will start from here, अगर आप यहाँ से start कर रहे हैं, or you can start from here, you can start from any point. If you start from here, 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 there are many possibilities. And we can observe from this motion that when x gets to maximum, suppose ये point है जहाँ से आप start कर रहे हैं, and this is the maximum value of x. When x gets to maximum value, p is 0, because p is 0 here. If p is 0, and what is p? P is x dot, and what is x? Dx upon dt. And what is dx upon dt? It is velocity. So if x is maximum, v is 0, velocity is 0, and when x gets to 0, अगर हमारा x 0 है इस पॉइंट के ऊपर, यहाँ पे x 0 है, then it is moving इस पॉइंट के ऊपर, x is 0, so your particle is moving with the most rapid momentum. So इससे हमें we found this. Now let's prove now energy conservation from Newton's equation. Here we found that in the circular radii, the radii tells us about the energy, and the different orbits have different energy. Now we will talk about the conservation of energy, and we will use Newton's equation for the same. Let's in one dimension, we will always think of any function. This is a function which is one dimension is equal to minus dv upon dx, where v is the potential energy. So we can write it like this: fx is equal to minus dv upon dx. And how can you find v here? You can find the v by integrating fx. So v is equal to, potential energy is equal to fx dx. Now how we have found this equation, fx is equal to minus dv upon dx. कैसे आया ये कि force is equal to minus of dv upon dx. Now find how we got this equation. For this, suppose your particle is moving in the x direction like this. It is on the hill. हिल की तरह या कोई हिली प्लेन है, वहां पे पार्टिकल जो है is moving like this. And it is moving along x-axis, and through a series of hills, this, and the altitude of it is roughly v, which is a function of x. The higher the altitude, if you put the particle on the hill over here, or you put the particle here, you can put the particle here, you can put the particle over here, so it means there will be force over here. If particle is here, because there is a relationship between the potential dv upon dx, and dv upon dx tells us the slope, this is the slope, so it means at this particle there is some force, and the effective force is in the x direction, and it is going to accelerate. If particle is here, if it is moving here, then it is going to accelerate. Which way you want to accelerate? If it is going here, then accelerate in this direction. If you will accelerate here, then it will be back here. So force on every point, force on that point, force on that point, force on that point, pushing you to the smaller v. How? अगर यहाँ पे force है, then you know that if will apply, if the particle is here, it will be accelerate here, though it is pushing it in the direction of smaller v. Here the v is small, v is little. So force on every point pushing you to the smaller v, that's why negative sign is here. And dv upon dx showing us the slope of the hill. At the top of the hill, this is the top of the hill, this is the bottom of the hill, there is no slope. So it means dv upon dx is equal to 0 at the top of the hill and at the bottom of the hill. So it means no force is here or here. It is similar that here is no force, or at the top is there is no force, and at the bottom there is no force. Let's prove very simple theorem from here, and that simple theorem is kinetic energy plus potential energy is equal to total energy, which is half mv square plus v of x is equal to E. Or we can also write it as half m x dot square plus v of x is equal to E. Or you can also write it as t plus v is equal to E. Now let's prove that t plus v is conserved. Or conserved means it doesn't change with time. Let's again look at this picture. You can see from this picture that rolling down from the hill, the potential energy will decrease. If the particle is here and it is rolling down from the hill, it means its potential energy will decrease. And of course, this particle kinetic energy will increase. अगर पोटेंशियल एनर्जी डिक्रीज हो रही है तो वेलोसिटी ऑफ द स्पीड यहाँ से जैसे ये नीचे जाएगा तो बहुत तेज मूव करेगा, तो इट मीन्स काइनेटिक एनर्जी विल इंक्रीज and potential energy will decrease. H is 0 and Fp is equal to mgh, we know it. तो हाइट कम हो रही है, नीचे जा रहा है, इट मीन्स पोटेंशियल एनर्जी इज डिक्रीजिंग वाइल वेलोसिटी नीचे बहुत तेजी से नीचे आएगा जब रोलिंग डाउन द हिल, तो काइनेटिक एनर्जी क्या है, इंक्रीज हो रही है एंड पोटेंशियल एनर्जी इज डिक्रीजिंग. So we can qualitatively say that if potential energy decreases, kinetic energy increases. But at this point C, अगर हम इस पॉइंट C पे देखें, यहाँ पे पोटेंशियल एनर्जी अगर ऊपर जाएगा, देन एज हाइट अगर ऊपर जा रहा है, देन पोटेंशियल एनर्जी विल इंक्रीज एंड काइनेटिक एनर्जी विल डिक्रीज. So from this picture we can say that total energy is conserved. So we should keep in mind from looking at this picture, and it will be helpful for us to show that total energy of the particle does not change with time. Let's write Newton's law of motion. And what is Newton's second law of motion? That is Fx is equal to mx double dot. Or we will prove from this equation that total energy is conserved. And how can we check? We just have to find the time derivative. And we know if time derivative of any quantity, suppose f is 0, it means that quantity is conserved. Now our total energy is a function of kinetic energy plus potential energy. Vx is equal to E. Let's find the derivative of this equation. How can you find the derivative of this equation? First derivative, we know it will be half twice mx double dot x dot plus d by dt of Vx, where V is a function of x and dE upon dt. Or it can also be written as mx double dot x dot plus x. This can be written as, because V is a function of x, it can also be written as dv upon dx and dx upon dt is equal to dE upon dt. And what is dx upon dt? It is equal to x dot. So you can take x dot here can be common. So x dot mx double dot plus dv upon dx is equal to dE upon dt. And according to Newton's second law of motion, mx double dot is equal to force. And what is dv upon dx? We have written it as, and prove from the equation graph also, that f is equal to minus of dv upon dx. So it is a mass time acceleration or force, and it is also a force but negative. It means this term is equal to 0. So if this term is left side is equal to 0, so it means right side dE upon dt can be written as dE upon dt is equal to 0. What does it mean? If dE upon dt is equal to 0, what does it mean? It means that our total energy E is conserved, or E is equal to constant, or we can say from using Newton's second law of motion, our E total energy is conserved. But this we have taken for one particle only, and which is moving in one dimension only. So what happens when there are more dimension of space? We are sticking here only with one particle at the moment, but more dimensions of space. And we can say that the dimension of space are x, y and z, that our particle can move to x, y and z. So we want to write vector equations for the same. So vector equation, we know that it has components, and it can be written as f sub I, where I can be x, y, z, any dimension, and it is a function of x is equal to mi xi double dot. This is the Newton's second law of motion for one particle, but that particle can move in 3 dimensions. It can move here, it can move here, it can move here. One particle can move in 3 dimensions, and we have taken I here. Now x here depends upon all the components of position. So this x can stand here, x, y, z, means all components of force in all directions. It means Fix means Fx, Fy and Fz. It means force of a particle in all directions. Iska is the meaning of this Fix. It means force in all 3 direction or dimensions. And we know Fix is equal to minus of, now here will be partial derivative, not simple derivative, partial derivative dv upon dxi. In other words, wherever you are, the component of force, if you are here, or if you are here, wherever you are, the components of force is proportional to the rate of change of potential energy along that particular direction. If you are here, it means if direction में move कर रहे हैं, then Fix या Fx is equal to partial derivative of v in the x direction. If here, partial derivative of v in the y direction, here then partial derivative in the z direction. So from this we can prove conservation of energy of one particle moving in many dimensions. How? We have already proved the particle conservation of energy of a one particle moving in one dimension. Now we are proving the same in many dimensions. What we will do, we will just sum here. Here the equation was half mx dot square plus Vx is equal to E. What we will do now, we will summation of I half m xi dot square plus Vx is equal to E, which means that here kinetic energy is sum of half of mass multiplied by square of its total velocity. Xi dot means total velocity in all the dimension, or we can also write it as xi dot square is equal to x dot square plus y dot square plus z dot square. V is still one function of position, and this is the total energy. Now we can write this equation as, now we because we are interested in finding or we are interested to show that energy is conserved or not, so we will again derive it with respect to time. So first time derivative, summation of I half m twice xi double dot xi dot plus del v upon del x1 dx1 upon dt plus del v partial derivative with respect to x2 dx2 upon dt plus del v upon del z1 dz2 dx1 x2 and dx3 and dx3 upon dt. What about the potential term here? potential energy term here, the total time derivative of potential energy is equal to V. If you move along x direction, then it means it is x1 direction times the rate at which x1 is changing. And if you will move around 2, it means rate of change of V with respect to x2 times the rate at which the x2 is changing, so forth and so forth. Now, what is the result of this equation? We can use I notation here as a sum. We can take summation of I out, and here also you can write it as xi dot. So here you can write it as summation of I m xi dot can be taken out, double dot, plus del v upon del xi. Instead of writing x1 upon x dx1 upon dt, dx2 upon dt, you can write it as del v upon del xi and xi dot. इस पूरे की जगह you can write it like this expression. So it means xi dot can be taken out, and this is the expression, and it is equal to total energy dE upon dt, or you can also write dEI upon dt. So what is inside the bracket? Here it is the mass time acceleration. It means it is force, and it is again the force of one particle in all the dimension. So it is the same earlier equation that we have written, just we have decorated that equation with I, means which tells us sum over one particle in all dimensions. So it tells us the derivative of energy, this term is equal to 0. It means derivative of total energy is equal to 0, or we can say total energy is constant or conserved. Now what happens if we have lot of particles? अभी हमने कितने लिए? We have taken one particle, then we have taken one particle in 3 dimensions. Now what will happen if we have number of particles? So we will do exactly the same things. How? We can describe the bunch of particles by writing x1, x2, x3, where 1, 2, 3 stands for the particles, not for the direction. ये 1, 2, 3 directions के लिए नहीं है, particles के लिए. And then y1, y2, y3 for the second particle, and similarly z1, z2, z3, and it can be written as so forth and so on. So all the coordinates of all the particles, we have labeled them as xi. We can write the equation just like earlier, but now we introduce the term mi here. Earlier we have not used mi. So mi means the different particles have different masses in general. But if we will take, it can also be written as this is x1, x2, x3, y1, y2, y3, and suppose we are taking one particle, that will be x1, y1, z1. One particle in 3 dimensions. One particle means one here in 3 dimensions, and another particle x2, y2 and z2. Another particle in 3 dimensions, so forth and so on. So if we will introduce mi, it means इसके लिए, for this the mass will be m1. It means mi means different mass for each 3 n coordinates. But of course we expect the mass of first particle is same no matter in which direction the first particle is moving. It is the mass for the first particle, this is the dimension for the first particle. So if the first particle is moving here, here or here, but the mass m1 will remain same. But there is the possibility that agar second particle is there, that its mass can be m2. But all the for one particle, if it moving in the another dimension x, y, z, m2 will remain same. So now we are introducing the term here mi. So what we will do? We will just put mi in earlier equation. Earlier equation क्या थी हमारी? This was our equation. What we will do, we will just introduce mi here and get the same results. Means वही हमारे पास बिल्कुल वैसे ही हम इसे करेंगे and we will get that the energy is conserved. It means total energy will be conserved. For many particles, suppose bunch of particles, ये rod है बहुत सारे particles से बनी हुई है, many particles moving can be any dimension, but the total energy will be conserved. Let's take the case of the spring to prove it. We know for the spring, अगर कोई spring हो, हमने last time भी किया था कि उसकी energy F force क्या होता है उसके लिए, F is equal to minus kx. For the spring, F is equal to minus kx. क्यों? ये इस तरह से spring है, यहाँ particle है m. If it is moving here, it will come back. K is a spring constant, then F can be written as F is equal to minus kx. And F can also be defined in terms of V, and we know F is equal to minus of dV upon dx. And we know potential energy, you can define potential energy from here. V is equal to minus of F dx. If F is equal to this, तो V निकालना है तो हमें क्या करना पड़ेगा, इंटीग्रेट करना पड़ेगा. V is equal to minus of F dx. So what is the value of F? It is minus kx, then minus minus plus, and अगर आप इसे इंटीग्रेट करो x square by 2, then the answer will be potential energy will be half kx square. It is potential energy. And we know what is the value of the kinetic energy. Kinetic energy is equal to half mx dot square. So it means total energy is equal to half mx dot square plus half kx square. For simplicity, we can take m is equal to 1, k is equal to 1. M is equal to 1 and k is equal to 1. So it means half x dot square plus half x square is equal to E. So we can say that this is the total energy. Total energy is the sum of the squares of the velocity. This is the velocity and position. So this is the origin of the fact that the particle is moving in a circular orbit. अभी भी हम इससे पहले भी हमने अभी इसको डिफाइन किया था. यही equation earlier we found that the same equation which tells us that our particle is moving in a circular orbits, and circular orbits के लिए उसकी C energy जो है, हर radii energy is constant and depends upon the radii. It means that particle is staying on orbits, यहाँ particle है, of constant energy. This is the constant energy. It means particle is staying on the orbits of constant energy. In fact, energy increases as you move away from the center. So it shows us the energy conservation. And these orbits are nothing but the contours of constant potential energy. In general, any particle moving in one dimension, it moves on a constant x dot square plus Vx. Why? Because E is conserved, E is constant. So it means any particle is moving on the curves of constant x dot square plus Vx. Vx may be more complicated. It means it moves on the contours. These can be contours. It moves on the contours of constant energy but in xp plane. हर एक पार्टिकल की यहाँ पे एनर्जी क्या है, कांस्टेंट है, because we have shown that the energy is conserved, total energy is conserved, it is x and this is p, phase space. So it moves on the contours of constant energy in x and p plane in phase space. So it moves like this. So this is energy conservation. It's just like we talked about in our first lecture that system might have cycles and each cycles has conserved quantity. We have given dice के केस में हमने quantities को 0 दे दिया था. Suppose 1, 2 move from here to here, here to here, here to here. Then हम अलग अलग सभी को एक value दी थी. It is just like that. Each cycle has conserved quantity. Let's talk about moment of conservation now. First talk about Newton's first and second laws. Newton's first law is the absence of force is the thing moves at a constant velocity. And the Newton's second law is the presence of forces. The force is equal to mass time acceleration, where d2r over dt square is an acceleration. And the first law is just a special case of second law. It can also be written as m dv upon dt is equal to f vector. If the force is 0, the velocity is constant, because then dv upon dt is equal to 0. It means velocity is equal to constant. So now let's talk about Newton's third law. It says that if one object exerts force on another object, then that another object also exerts equal and opposite force to first object. If this A will exert force on the first object, then B will also exert equal and opposite force to A. Let's make an assumption that everything is made of point particle. Suppose this is one point particle A and this is another point particle B. The force of A on B, or the force of particle 1 on particle 2. Suppose this is one particle or two particle, or we can assign it as A and B. So suppose we label the particles I. I equals 1 no matter how many particles there are. So the force on I due to J is equal to minus of f ji. It means force on J due to I. It is equal and opposite force. It means force exerted by J on I. This is force on I due to J, and this is force on J due to I. The force is suppose this is the equal and opposite force, or we can say this is a Newton's third law of motion. If the forces are along the line of centers like this, so it means there will be equal and opposite, but they are pulling forward और अवे फ्रॉम ईच अदर. अगर यहाँ पे है तो मे बी ये इक्वल एक दूसरे को पुल करेंगे या एक दूसरे से दूर जाएंगे. लेकिन अगर इट्स अ स्टील रॉड, इट कांट एक्सपेंड और कॉन्ट्रैक्ट. सपोज वी हैव अ होल बंच ऑफ पार्टिकल्स. And let's label them I. And this is a closed system. Here is nothing else in this system but these particles. So no external forces from other objects. Only the forces of particle on each other. तो बाहर से कोई फोर्स नहीं लग रहा, क्लोज सिस्टम है, बस पार्टिकल्स एक दूसरे के ऊपर, ये आई जे के ऊपर लगाएगा, देन जे आई के ऊपर, जे के ऊपर, के एल के ऊपर, एल आई एल. सो ओनली द फोर्सेस ऑफ पार्टिकल्स ऑन ईच अदर. सो वी कैन राइट मास ऑफ ith पार्टिकल टाइम्स द एक्सेलरेशन mi टाइम्स द एक्सेलरेशन d to ri upon dt square is equal to summation of all other particles where j is not equal to I, or we can say it is equal to Fij. We have taken j is not equal to I because particles don't exert force on themselves. That's why we have taken j is not equal to I, क्योंकि एक पार्टिकल एक दूसरे के एक ही पार्टिकल आई के ऊपर नहीं लगाएगा, अपने ऊपर नहीं लगाते. So we can also write it as mi dvi upon dt is equal to, it can also written as dpi upon dt is equal to summation of j is not equal to I Fij, or it's just the derivative of the momentum of ith particle. What is this? This is the derivative of the momentum of ith particle. And the force is I derivative of, so force क्या है? Force is I derivative of momentum. So obviously this is the equation for each I, like 1, 2, 3, 4 up to many particles there are. Let's add up all of the equations for all the particles. So then left side, अगर हमने सभी को ऐड कर दिया, then this left side will tell us the time derivative of sum of all momentum, or we can also write it as d by dt of p total is equal to summation I comma j f I j. Total momentum of all the particles it tells us, and here sum over I and j. Now what do we get now on right hand side? We get 0. Why? Because each pair of particles is counted twice. Ij, ji, jk. अगर ij है, then one force is ij, then another force will be fij, then another force will be minus fi. If one force is fik, then another force will be minus fki. If one is I jk, then another will be minus f jk. So the right hand side gives us 0. So when we add up all of the forces of all the particles, they add up 0 because they come in equal and opposite matched pairs. So the result is from Newton's third law is that it is equal to 0, or it is equal to 0. dp total upon dt is equal to 0. We can also write it again, dp total upon dt is equal to 0. So what does this say? That the total momentum is conserved. If derivative of differentiation with respect to time is 0, it means P total is equal to constant, or we can say it is conserved. Because differentiation of any quantity is 0, it means that quantity is constant or conserved. This is momentum conservation law, or we can say total momentum is conserved as a consequence of Newton's third law. That's all for today. In next lecture, we will discuss principle of least action, which is another formulation of mechanics that will go to Lagrangian and many other interesting things that will take us into more advanced aspects of mechanics, or we can say classical mechanics. But before leaving, if you have not subscribed my channel, please subscribe and share also. And if you have any doubt or any query, you can mail me at the email ID given in the description box, or you can also write a comment in a comment section. Thank you so much.